Before we start, give everybody another minute to get here. I will remind you that Mesh runs some workshops and services for you, which can be found on the Mesh page. If you Google WSU and Mesh and events or workshops, you'll get there. If your computer is faster than this, this is the slowest computer in the world. And you'll see there, right up the top is Mesh Team Roving, that's library roving. And you can see the hours at the various campuses where there is someone in the library, except in Parramatta City campus, they're on level 1, who you can drop in and work with them and get a bit of help if you want. Then there's, if we close that little box and scroll down, we will see there is Discrete Maths workshops. That's you. So that's class test preparation. Let's see, Campbelltown has already had theirs, but look, next week. Anybody registered for this yet? Good. Are you going to go? Good. Pleased to hear it. That's only one small part in your preparation, but it's an extra hour's work with some stuff to go away with. Yes?
See how they have one mesh after the other? Is there any point to doing both of them, or do they teach the same thing in each one?
It's the same thing, but they've got a sample test. But a lot of people have problems, to go through everything thoroughly for a lot of people will take more than an hour. And so it's a good idea to go to a couple of them if you want, if you really want to spend your time over it and ask and talk to people if there's things you don't understand. Because sometimes if you find a bit you've missed, it can take you a good quarter of an hour to sort of start to get your head around it. So it's up to you, but you're certainly welcome to attend as many as you want. So that's help for you. Yes?
Is there any past papers like at the library or something, or whatever you guys give us?
It's just what you get from us. Now, what's the best way to prepare for the test? Tutorials. That's right. It's not past papers. Tutorials. Yeah. So the sample test, there is a sample test. I saw James's note about that. There is one. As he said, the questions will be different to the actual test. So the sample test is not the best way to prepare. It's a way to test yourself to see just overall how you're going. If you start with the sample test, you're doing the wrong thing. You're not using it in any reasonable way to prepare. It should be towards the end of your preparation. And Mesh will have a sample test, but theirs is sort of designed to, work you on concepts that they think are useful for you to have. And they don't have no idea what James has set in the real test anyway. So, and that's it. There's no other sample tests around. Okay, any other questions? I think there was some statistical decision-making things. Look, statistical decision-making, that's relevant to some of you, I know. There's a whole lot of stuff. This page is updated. This page is the events page, events, workshops and programs. This is updated very regularly because the Mesh program is dynamic. Okay, now we have a lecture for today. And we have screen. It's more on counting. And that's good because counting's a lot of fun. I love counting. You can get some really easy counting problems, but gee, you can get some hard ones. You can get incredibly, incredibly hard counting problems. You've got the whole lot, and you can have problems that are a lot of fun. You can have a huge amount of fun with counting. Anyway, we did a little bit on counting last week. We did the addition and multiplication principles. And I found out you've been doing some stuff we're doing today or last week in statistical decision making as well, just for those of you who are doing statistical decision making as well. Anyway, we're doing, we did inclusion exclusion. We looked a little bit about functions and counting the number of functions, number of injective functions. Surjective is a little bit harder, but someone has sent a solution to counting's number of surjective functions. If any of you feel like also working that out and sending to me, I'd love to see it. Permutations. And this week we're going to continue on with things, unordered selections, binomial coefficients, and so on. So what I want to do now is move on to the projector so I can scribble, because I like scribbling. Okay. So we have a problem, a simple counting problem. From a class of 30 students, a committee of 3 is to be chosen. There'll be a president and a secretary and a treasurer. Now, in this question, those 3 roles must be filled by 3 different people. In how many ways can this be done? Okay, and then there's the same question, but it's possible for a student to take on more than one role. 2 different questions, 2 different answers, of course, because they're different things. The number of answers here is greater than from here. And we worked out what that was last week, and you might like to think about it again, see if you remember what you've done last week. But these involved ordered selections, in that ordered in the sense that if Jane is president, Joe is secretary, and Jean is treasurer, it's different to if Jean is president and the other 2 take the other roles. It matters who is president, who is secretary, and who is treasurer. If you swap them round, that is, if you change the order, you get something different. And so you count it twice. If you've got as president, secretary, and treasurer, if you've got Joe, if you've got, who did I have? Never mind. Person A, B, and C, that's different to having persons A, C, and B. So if it's a different order, it is a different committee. And so we count them as different. Order is important. That's an example of ordered selection, where the order matters. Now, in these 2 examples, we have a difference with repetition. In the first question, when we have the president, the person chosen for that can't be chosen again. We've got to have a different person for secretary and then a different one for treasurer. We're not allowed to have repetition. We're not allowed to repeat our choice. So we can't have Joe as president and Joe as secretary. So that's without repetition. Repetition not allowed. In the second question here, repetition is allowed because a student can take on more than one role. So it's okay for Jane to be president and for Jane to be secretary, and perhaps even for Jane to be treasurer. So we're allowed to, when looking at a role, repeat the choice we just made if we want. That's with repetition allowed. So you see the difference? If you're allowed to repeat, as you'll see in this example, we ended up with a different answer. So for some questions, a question of this sort, you'll want to know if the order matters, if it's an ordered selection or unordered, and you want to know if repetition is allowed or not. Now, ordered selections, which we did last week, from n things, with repetition allowed is equal to n to the k. That was last week. So if you've got your 30 students and you're looking for the 3 positions, you've got 30 choices for president. You're allowed to have the same choice again, so you still can choose any one of the 30 people for secretary, and you can choose any one of the 30 people for treasurer. So the number of choices by the multiplication principle is 30 times 30 times 30. And that's the n to the k. So you're choosing 3 people from n available people, so it's 30 cubed in that example. That was last week. But then when it was with repetition, and you're choosing, with repetition not allowed, without repetition, you had 30 choices for the president, but because, say, you chose Jane, Jane or whoever had been chosen could not be chosen again. You can't repeat the choice of Jane. You've only got 29 choices for the second position and 28 for the third. So the answer in that case was 30 times 29 times 28. And that's the 30 times 29 times 28 is we start at 30 and we go down one step at a time till we've got 3 terms, and that's the falling factorial, 33. That was from last week. 30 lower brackets 3, not 33. Okay, so that's ordered selections with repetition allowed, ordered selections without repetition. What if we don't care about order? So, yeah. Okay, so we're just looking for a committee of 3 people. Just 3 people to I don't know, do whatever. Organise all the social events for the class, I don't know. All right, so we're choosing 3, but this time order is not important, because if I just want 3 people and I say we'll have Jane, we'll have Joe, we'll have Jean, it doesn't matter if I choose Jean first and then Joe and Jane, we've got the same committee. There's no sense of order this time. Do you see the difference from what we did before? Think about it. We've just got a set of 3 people. And you know with a set, it doesn't matter in which order you write the elements, it's the same set. And that's the sort of thing we're doing here. A committee without any special roles like president or whatever, but just a committee is just a set of people. So we're choosing a set. Order is not important. So let's think about how we'll count the number of committees there are. If I choose Jane, Joe and Jean, and you choose Jean, Joe and Jane, it's actually the same committee. So, and if we want 3 people, if I've chosen Jean, Jean's in the set, I can't choose her again because she's already there. I need 3 different people. Otherwise, I'll have a committee of 2 or 1. Okay. So let's imagine we're going to choose this by doing it in 3 steps. It's always a good idea to break up a problem into pieces if you can, and we've seen the advantage of having several tasks, and the multiplication principle makes counting easy if you can do task 1, task 2, etc. We have 3 tasks. Task 1, choose the first member, any of the 30 people in the class. Task 2, choose the second member, because we want 3 in total, it's got to be someone different, so there'll be 29 choices there, and choose the third member, there's 28 people you can choose there. But this is, it overcounts, because you've counted choosing Jane, Joe and Jean to be different to Jean, Joe and Jane. If you've selected the committee in a different order, you still get the same committee, but you've counted them as different. So our number, this is too big. We can fix it. Okay, we can fix it. All right, so this is sort of saying what I've said with different names. Jane's popular though, isn't she? If you made your choices Bob, Jane, Sarah, or Sarah, Jane, Bob, you get the same committee. And that's why it's overcounted. You've counted that once, twice. In fact, what if you'd done Sarah, Bob, Jane? Gee, you would have counted that same committee 3 times. In fact, you'll have counted that same committee quite a few times. Any committee of 3 people gets counted many times. How many times? How many times will I count the committee consisting of Bob, Jane and Sarah? At least 3, because I've got 3 factorial. Yes, because I could have, the number of ways, different ways in which I can write this out in order is I could put, I've got 3 choices for the person whose name is first, 2 choices for the person whose name is second, and then there's only 1 thing I can put here for the person whose name is third. That's 3 factorial, which is 3 times 2 times 1, which is 6. That same committee will have been counted 6 times by the method on the previous slide. So the answer is wrong, because every committee has been counted 6 times, but we can fix it because every committee has been counted 6 times. And that's the 3 factorial ways in which that committee will be counted. And 3 factorial, okay. So right at the bottom of this slide is how we fix it. We've counted every committee 6 times. We just take our number and divide by 6, right? Yeah, it's the same as, let's say I decide to count the number of people in this room, and I decide to do it by counting feet. 1, 2, 3, 4, 5, and so on. And I get, let's say I get, I don't know, let's say I get 100. How many people would be in the room? Because I've counted every person twice, right? Yep. Okay. Good. Same principle. Every committee has been counted 6 times. The Bob, Jane, Sarah committee has been counted once, twice, 3 times, 4, 5, 6 times. So we take the number we got here, where we counted them as though it was ordered, which meant we counted each committee 6 times. So we divide by 6 to get the correct answer. And that works. It's the same as counting the number of people in this room by counting the number of feet. I'm assuming you all have 2 feet. If you don't have real feet, you've got prosthetic feet and they're just as good. Okay. Make sense? So we can count now some unordered selections. We've just learned how to count unordered selections with no repetition. This is the same question. How many subsets of size 3 does a set of size 30 have? Well, I said a committee is just a set of 3 people, so it's just the same question. It's exactly the same question. The set is 30 and the committee is 3, that's the subset. So an unordered selection of k elements from a set A without repetition is just a subset. So let's say we're choosing not just 3 students, but k students from a set A. We're just choosing a subset of size k from the set of all students. This is unordered because a committee is unordered, and there's no repetition because I do want to end up with k students, so I've got to choose k different elements of the set, k different people. So this is unordered without repetition. Okay. How many 2-element sets of 1, 2, 3, 4 are there?
4 choose 2.
All right, yes. Now I want to do that thinking about what we're doing here. I want to get there step by step. Let's see if you can do this one. Can you write down, with the thinking we did for the committees, how many 2-element subsets there are of 1, 2, 3, 4? I want you to do the same sort of thinking. Give you a little bit of time to think about it. Answers? 6. Okay. Let's see if I get the same answer. I'm looking at choosing, first I'll just see how many ways there are of choosing 2 elements. How many choices do I have for the first element? 4 choices. How many choices do I have if I choose a second element? By the multiplication principle, that's 12. But have I overcounted? I have, because I've counted the choice of choosing, say, 2, 4 as 2, 4, but then I've got it the other way around, 4, 2. So I've overcounted twice, haven't I? So the answer is 4 times 3 divided by 2, which is 6, and you're all right. Okay, so you can do the same thing here and here. So this tells us, I think we've looked at this a couple of times, we should be able to find a formula for the number of k element subsets of an n element set. And the notation used for this, the number of k element subsets of a set of size n, is nk, and we read it as n choose k. And you've probably seen it, if you've seen it before, it's most likely you've seen it as one of these things here with the C. Has anybody seen one of those before or that? Hands up if you've seen this before somewhere. Good, okay. Was it in statistical decision making? Yeah. Okay, so you know all about it. Oh, except you're not all doing statistical decision making. I know there's quite a few in here who aren't. All right, the C is for choose, actually, choose. N, choose K. It's called a binomial coefficient, and that will be explained a little later. So don't worry about that. You'll see that the reason it's called a binomial coefficient is it's a coefficient in a binomial. Sort of makes sense, doesn't it? Okay. But we haven't got a formula for that yet, except some of you will know what that is. That's great. Here's a reminder. And for those who don't know, here it is. So we're going to consider in general now, not just the 3 students from 30, but choosing K things from N. It's ordered as it was in choosing the committee. Wait a minute, we're starting out with ordered, which wasn't the idea of the committee, but we're just going to start out that way, just as we did with our example, and then we'll discover we've overcounted and we'll divide by something. So we're starting in the same direction, even though we're headed for unordered, because we know the ordered thing we can do really easily. That's from last week, of choosing K things from N. It's N for the first times N minus 1, because it's without repetition, times N minus 2, and so on. So that's what we've got there. The number of ways of choosing K things that's ordered is this, because you do it as K tasks, and there's your number. But we know there's overcounting. We know we've got to divide by something. Okay. All right, so we're going to sort of go backwards to find out what we're going to divide by, but it'll come out in a moment. We're going to do the ordered selection now in a different way. We're going to make an unordered selection. We don't quite know how to do that though. We're sort of heading towards it. Never mind. And then we're going to put these elements in order. All right, this is a bit backwards, but the number of unordered selections, we've given a name to it. It's always good to give a name to something you don't know. It gives you something to write down, also makes you feel like you've done something, and it impresses people, okay? So we've got this name, we've got this symbol, N choose K. It's the number of ways of finding an unordered selection. We don't know the formula yet. Don't worry about that, it's coming. Okay, so let's say I want to take my committee of 3 people, and I actually want to do an ordered selection by choosing President, Secretary and Treasurer. So this time I'm doing it in a different way to last week and the start of this lecture. I just grabbed 3 people. Right, here we are, 3 people. The number of ways of choosing 3 people from 30 is 30 choose 3. And in the second step, I say, right, I've got my 3 people. I'm going to have you for President, you for Secretary, and the last one will be Treasurer. So that's a 2-step way of choosing a committee. It's a different way of choosing a committee with President, Secretary and Treasurer from last week, but it still works. Okay, so for the second task, when we've just got this set of people and we want to put them in positions, President, Secretary, Treasurer, or if we've got K things and we want to line them up and put them in order, the number of ways of doing that is K factorial. Because if you've got a set of K things, you've got K choices for the first one, it's gone. K minus 1 choices for the second, K minus 2 choices for the third, and so on. That's K factorial. So by the multiplication principle, the number of ordered selections, the number of ways, if you like, of choosing a committee with everybody having a role is N choose K times K factorial. And that is really nice because these 2 things, this one here and this here, answer the same problem. This was the number of ways of making an ordered selection of K things from N. This was also the number of ways. It's just that we did it in 2 different ways. You might want to go back and think about this after the lecture. But that means that number is equal to that number. And that is a common trick in this part of mathematics. You can learn things by counting something one way and then counting it another way, and you might get 2 different expressions that actually count the same thing. You've either made a mistake or the 2 things are equal. get it right, and sometimes you've learnt something. And that's what we've done here. We've counted things in 2 different ways. And so these 2 numbers, the 2 answers we got, because we haven't made a mistake, these 2 must be equal. And I'll bet that's on the next slide. Oh, yes, look, it's something like that. It says, we've answered, yeah, the 2 are the same, and that's it there. That's the big thing we got out of this, counting something in 2 different ways. Okay, now we know what that is, we know what that is, we don't know what that is, but if we make that the subject, we have a formula for it. So here it is. That equals the falling factorial divided by k factorial. So that gives us immediately that. And then if we write this out, I have a feeling I did something like this a lecture or 2 ago. But anyway, if you write it all out, you get that. But then there's nothing wrong with that. It's correct. It's beautiful. But we usually write it just a little more simply by mucking around a bit. I'm just going to multiply top and bottom by the same number. There's a fraction. If I do the same thing to the top and bottom, I don't change the fraction. So I multiply the top by the rest of the numbers down to 1. That's all the other numbers going down to 1. And I put the same numbers on the bottom. What I've got here is on the top, I've got n all the way down to 1, which is n factorial. And then we've got the k factorial there. And that is actually n minus k factorial. And that's n choose k. That's n choose k. Remember that. This is the thing you should remember. That's the number of ways of choosing a subset of size k from a set of size n. N choose k. Right. There it is. Summary. And that's summary again. This is just saying it again. This is just slide is just a repetition of what we've done. More repetition. Unordered selections, no repetition, because if we want k elements, then we've got to choose k things. If you choose fewer than k things, you've got repetition and you actually haven't got k things. Okay, so there it is. Remember that. And these numbers are called the binomial coefficients, but we'll just say n choose k. That's how we say it. So this is a summary slide. But you might like to think about how we got here, the last 3 or 4 slides or 5 slides. And if it's a little bit hard to think about in general, think about again the choosing 3 students from 30, or you might want to choose 5 students from 10 and think about that to make sure you understand it, because this subject is not about remembering formulas. It's about understanding and problem solving and thinking, being able to count and answer problems. I mean, the formula's great if you realise that a question is about unordered selection with repetition. Sure, bring that out, put the numbers in, that's great. But you're not going to get very far if you don't think and get your brain going. And I was reading something I've read several times before, but it reminded me of it a couple of days ago. People have been studying brains. I don't know how they do this, whether they chop up the heads of students or whatever, but I don't think they do, and I don't think they put electrodes in people. But you can do imaging, brain imaging, while people are thinking or working or whatever. And anyway, somehow, some clever people have worked out that you learn more when you make mistakes. If you do something, make mistakes, and then get it, you actually learn more than if you just get it right the first time. So I think the lesson there is to push yourself to the point where you start making mistakes, and that's the point where you need to start learning, and that's where your brain actually grows and you learn best. So don't worry about making mistakes. Making plenty of mistakes over the next week, especially preparing for the test, is fine. It's going to be good for you, especially if you then work out what was wrong and fix it up. I think the idea is you actually look at your mistakes and find out what you did wrong and work out what's right. You actually learn better that way. And if you can't work out what's wrong, that's why you email me, go see Mesh, drop in and see me, etc. Okay, now here's some questions. Let's do some quick answers here. We'll just do the first 2. I'll leave the last 2 for you. We've done this one, committees of 33 students from 30. That's 30 choose 3. which is 30 factorial over 3 factorial and 30 minus 3. This pen is being a pain. That's 30 minus 3 factorial, which is 30 factorial over 3 factorial, 27 factorial. All right. Now, if you're doing this in a class test, like for example next week. Oh, when's your class test? At what time? What was that? In the lecture? This time next week you'll be doing a test. Got that? If you're late, you're stuffed. Okay, so be on time. Be early. Okay. You can, once you're doing a question like that, you can just leave your answer like that. You don't have to work it out and work out that it's 5,000 or whatever it is. That's fine. That shows you can do it. All right, next question. Say we're doing a committee of 37. The same principle applies. It's 30 choose 27 is the answer because it's unordered, no repetition. And that is 30 factorial over 27 factorial, 30 minus 27 factorial, which is 30 factorial over 27 factorial, 3 factorial. What do you notice about the answer from these first two questions?
The reverse. If the lot, for example, if it's 30 over 27, it's exactly the same as 30 over 3.
It is. They work out the same, don't they? And you can see here at this step here, you end up with exactly the same, don't you? Yeah, they're equal. Yes. Yes, and you'll probably find the same thing there. So, question here, explain why n choose k is equal to n choose n minus k. There's a couple of really nice ways of doing that. It's actually quite easy. Firstly, you know the formula for n choose k because it's a couple of slides ago, and you can use that and it will work. Oops, what is that doing there? Okay. All right, let's continue. We've got 14 teams, and the top 8 teams will make the quarterfinals. Okay, there's all sorts of ways in which this can happen. How many possible quarterfinal groups are there? And that means how many possibilities are there for getting 8 teams? You're just going to end up with 8 teams. In how many ways can you get 8 teams from 14? Is this ordered? No. Good. Because you're just looking for a set of 8 teams, unordered. Repetition? No, because you want 8 teams. You're not going to choose one team twice. It makes no sense. No. Repetition. So somehow, I guess the competition will select 8 teams from 14. So we're selecting 8 teams from 14. Any ideas? 14 choose 8. It's what we've just been doing, isn't it? Yes, it's 14 choose 8. So it's 14 factorial divided by 8 factorial, and then we've got 14 minus 8 is 6 factorial. Okay, that's the answer to that question. What if ordered mattered? Say 8 teams are going to make the quarterfinals, but they make it ranked 1, 2, 3, 4, 5, 6, 7, 8, and people care about the ranking in which they end up in the quarterfinals. In how many ways can that happen?
14 factorial over 6 factorial.
Someone else? Yes, someone said there's several ways which you can say this. So some other answers. I heard a few, and then I heard a lot of mumbling.
14 choose 8 times 8 factorial.
Oh, there's another way of saying it. 14 choose 8 times 8 factorial, because this is what we just did. Nice. You take the unordered selection and then you rank them. So that's our 14 choose 8, which is 14 factorial over 8 factorial, 6, that's a 6 factorial, times 8 factorial, and then we can cancel the 8 factorials, giving 14 factorial over 6 factorial, which you might recall is 14 falling factorial 6, which is another way of doing it, of writing that, because it's ordered with no repetition. And that's from last week, the falling factorial. 14 times 13 times 12 times 11 times, etc. Or you could just write down straight 14 choices for the first team, 13 for the second, 12 for the third, 11 for the fourth, 10 for the fifth, 9 for the sixth, 8 for the seventh, and 7 for the eighth. And they're all the same. All those answers are correct, and they're the same. Okay. Think about this. Give you a little bit of time to think about how we're going to cope with that one. Ideas? Yes?
7 choose 4 times 7 choose 4. So what were we just do that twice to get?
Okay, yes. Yes, let's do it twice. Let's break this up into 2 steps. First, task 1, we take one group of 7, pick your group of 7, and 2 groups. So we take one group of 7, and the number of ways of getting 4 teams from that, because it's unordered without repetition, is 7 choose 4. And then you come to task 2, which is you deal with the second group of 7, and it's 7 choose 4. And you multiply them together by the multiplication principle. So the answer is 7 factorial over 4 factorial 3 factorial times 7 factorial over 4 factorial 3 factorial. There it is. And I'll leave you to think about what happens if ordered mattered, because that's sort of a combination of these 2 things, and it's really all here. Okay. Now, for those of you who like playing cards, a lot of this counting is useful for probability. So if you were going to look at the probability of various poker hands, or if you were looking at things like lotto, gambling, things like that, to work out probabilities, you need to look at the number of ways out of all the possible ways that you can get a straight or a flush or whatever these hands are. With lotto, you need to look at the number of ways you can get various numbers out of the whole number of possibilities. It's all counting. So let's take an example here. How many 5-card poker hands are there? Okay, so firstly, just in case some of you don't know, because I know that this is about cards, packs of cards can be different in different cultures. So what we're talking about is the standard 52 deck cards that are common in Australia. So you've got a hand of cards is basically just a subset. So when we say a hand of cards, it's just a set of cards. It's called a hand because you hold them in your hand. You've just got a collection of, in this case, 5 cards in your hand. It's just a set because there's no sense of order. It's a hand is a hand. If you get the cards in a different order, it's still the same hand. And the total number of cards is 52. There are 52 different cards. They're all different. And we're looking at how many sets of 5 there are. So how many 5-card poker hands are there? The poker is in there because with poker you have 5 cards. What we're really asking is how many sets of 5 cards can we get from 52? 52 choose 5. Yes, 52 choose 5, which is 52 factorial over 5 factorial. 52 minus 5 is 47, so that's 47 factorial. Okay. 4 of a kind. Well, there's the hands are actually, there's ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we got jack, queen, king. Now, it doesn't matter what these stand for. The point is that there are 13 different things here, and there are 4 of each. There are 4 different aces, 4 different ones, 4 different twos, etc., up to 4 different kings. That makes up the 52 cards. 13 times 4 is 52. 13 different kinds. Okay, now, if you get 4 of a kind, and that's supposed to be pretty good. I don't know how it ranks out of all the other hands you can get, but if you get, of your 5 cards, I'm holding 5 cards here, if 4 of them are the same kind, say 4 of them are 10s, or 4 of them are aces, that's 4 of a kind. So 4 of them are the same kind, and the 5th card, well, that's just going to be something else. How are we going to count the number of hands that are like that are 4 of a kind? Only 13?
Yeah, because you can have different variations because it's all 4 of the different tens. You can have different variations.
Right, so we're either going to have 4 aces, 4 ones, 4 twos, 4 threes, all the way up to 4 kings. There's 13. All right, that's most of the way there. What is the last step? The extra card, yes. All I can hear is mutter, 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 mutter. What do you think?
48 other possible cards.
There are 48 other possible cards, so what number do I write here? 68? 48. Yes, good, thank you. Okay, with a bit of work, we got it. Now, what we did was think of this as 2 tasks. Let's go back to the multiplication principle. Task 1. We get our 4 cards of same kind, and that means we take 4 aces or 4 ones or 4 twos. There's 13 possibilities. That's the 13. That was task 1. That gave us 13 because there are 13 kinds. And then that gave us 4 cards, but a hand has 5 cards, a poker hand does. So our task 2, get the last card or the 5th card. And with 4 cards of the 52 gone, there were 48 cards left. And it doesn't matter which one of those you take, you've got your 4 of a kind. So it's 13 times 48 with the 2 tasks. Does that make sense? Okay, thank you everybody. You got us there really fast. Good. Okay. Ooh, some exercises. I'm going to leave some of these for you to do. But do you remember what 0 factorial is? Hey, most of you do. I'm impressed. That's good. Very good. Now, if you're one of the ones who didn't remember what that is, don't worry. You've got plenty of time to practice and think about this. It's 1. What is 0 choose 0?
There's one way of choosing nothing for nothing.
Oh, I love that answer. Yes. Yes, there is one way of choosing nothing from the empty set, and that is do nothing. So it's 1. But you might like to do that using the formula because you now have a formula for n choose k. Let's see what the formula tells us. It's 0 factorial over 0 factorial, and then we've got 0 minus 0 is 0 factorial. That's 1, because 0 factorial is 1, over 1 times 1, which is 1. Oh, we get the same answer both ways, which we'd expect. Okay, good. What's 0 to the power of 0?
That's a bit of a trick question because you can't have 0 squared is still 0, so 0 times any number even to the power of 0. However, there have been arguments that it equals 1 because anything to the power of 0 is 1. So there's a video on YouTube. Okay, I'm going to shut up.
No, that's nice. That's yes.
Guys, don't fall for it.
No, that's nice. That's nice. It is. You've given the two arguments for saying that 0 to the 0 is 0 because we know that 0 times anything is 0. And you've given the argument for 1 because anything to the power of 0 is 1. So what do mathematicians do? Well, in most cases, certainly in the cases that we're working here, there is a strong argument for 0 to the power of 0 being 1. And here's a couple of arguments for it in these cases. If I'm not multiplying any zeros together, there's no multiplications actually happening because there's none of them. So we don't get 0 because no multiplication has happened. And when you've got nothing, you start with 1 with multiplication. Now, there's a lot of maths behind that, which I'm not going into. But so that's not going to convince you. But last week, I mentioned that we found out, actually, that the number of functions from a set of size A to a set of size B is B to the power of A, the size of B to the size of A. So the number of functions from, if I'm looking at functions from A to B, the number of those is the cardinality of B to the cardinality of A. That's the number of functions. So if I look at the number of functions from the empty set to the empty set, there is only one function. It's called the empty function because it doesn't do anything because there's no elements. So there's only one of them. So in that case, I've got 0 to the power of 0 and the number of functions is 1. So I'll put 1 there. Now, those arguments might not be particularly convincing. This is the sort of thing that's best to come back to after you've done a fair bit of maths and can read the various arguments in detail. But most of the time, I take it as 1 because that's what it should be in the sort of maths we're doing here, and that's the sort of maths I deal with most of the time. Okay. Now, these ones are easy. Just stick it into the formula and you'll work it out. So that's up to you. It's a good exercise to do this, to calculate all the numbers nk for all values of n up to 5. There aren't that many of them. There's something for you to do on a rainy day, but we're actually coming to something that will do it for you easily. How many of you have seen Pascal's triangle before? A few of you have. Oh, well, those of you who haven't, it is great. It is so much fun. And you can do all sorts of things beyond Pascal's triangle, including colouring it in and get wonderful patterns and stuff like that. There is so much you can do. But we're just doing the traditional, the classic Pascal's triangle. We write 1s on the sides. There's a reason for this, but for the moment we just put 1s on the sides. There's our 1s. That's the first bit. I've put our 1s in there. Okay, now we calculate every other number in Pascal's triangle by looking at the 2 above it, because there's no number directly above, but there's one above to one side and one above to the other side. So to calculate this number here, we look at the 2 numbers here. We write them. It's I'll put them here, 1 plus 1. 1 plus 1 is 2. So I add those 2 numbers and I get 2. To calculate this number here, I look at the 2 above. There's 1 and there's 2, and I add them and I get 3. Okay? What do I get here? 3, because I get 2 plus 1. Does that come out here? Sort of. That's 3. Okay, what number goes there? 4. 1 plus 3 is 4. What number goes there? 3 plus 3 is 6. What number goes there? 3 plus 1 is 4. And here? There? Okay. Now you might think you're back in primary school, just playing around with numbers, but yeah, kids have a lot of fun in primary school. What's wrong with it? But the other thing is there's a lot behind this. And you can keep on going forever. See those dots there? Do they show up? Big dots. You keep on going forever. All right, that might be a bit of fun. But let's not forget this, okay? We'll put this aside, but we'll come back to it. You know, those lovely numbers, the 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. You might have seen those numbers before anyway. We'll put them away. We'll come back to them. Okay, let's do a bit of expanding. X plus 1 squared. You all know that's x squared plus, what's the coefficient of x? 2 plus 1. Okay. X plus 1 cubed. Can anybody tell me what that is? X cubed plus? Wow, you guys haven't done much expanding of these things in your life. When I was your age, I knew these. What's happened to the youth of today? Did someone say 3x squared? Thank you. How many x's? Too many. No, it's not too many. It's only 3 plus 1. I'm going to have to do all these for you, aren't I? Good grief. Warning, I am not going to do your test for you next week. I'm going to have a relaxing 45 minutes with my feet up here reading a book while you do your test. So you're going to have to do things yourself at some point. All right, x plus 1 to the 4th is x to the 4th plus 4x squared plus 10x plus cubed, 4x cubed plus 10x squared plus 4x plus 1. It's some of you do know what's going on. Thank you so much. Where would I be without you? I'd be in a big mess, wouldn't I? That's great. Of course I know it's... Okay, thank you. See if I get this one right. Plus 5x to the 4th plus 10. I knew there was a 10 somewhere. I'm up to x cubed. 10x squared plus 5x plus 1. Okay, that's the answers to those questions. 1, 2, 3, and 4. Do those numbers, the coefficients there, look familiar? What are the coefficients here of x? That's 1x squared plus 2x plus 1. That's 1x cubed, 3x squared, 3x plus 1. 1x to the 4th, 4, and my 6, 4, 1. Have you seen those numbers before? Okay, you have. They're the numbers in Pascal's triangle. And if we want to look at, let's put in a question 0 here, and just note that x plus 1 to the 1 is just x plus 1, which has coefficients 1 and 1, and that actually gives us that line there. And x plus 1 to the 0 is 1. So we see the coefficients 1, 1, 1, 1, 2, 1, the 1, 2, 1, 1, 3, 3, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Damn, it's gone off the, sorry. There's the numbers, 1, 4, 6, 4, 1, 1, 4, 6, 4, 1. You can see each row corresponds to the coefficients. See that? Isn't that nice? It's not the most amazing thing about Pascal's triangle. There's so many other things. Just for 2 seconds, just for a bit of fun, just for a little bit of fun. And maybe we'll do it later. It might be down on a cheat sheet or something. I don't know. Yeah, let's do it. add up the numbers along the row. What happens, say, if I add up all the numbers along this row here? What do I get? Add them up. What do I get? 8. What do I get if I add up the numbers along this row? What do I get if I add up the numbers along that row? 32. Ooh, that looks like a pattern. What if I did it with this row? That's an easy one. 5? 4. And this row? And this row? Do you see a pattern? Yes, powers of 2. Yes. Okay, that looks interesting, doesn't it? I wonder why that's true. Oh, there's a problem for another day. And there's other things there. You can take the alternating sum of... There's all sorts of fun you can have with that. Okay, but let's concentrate on this, which is the coefficients you get when you expand a binomial. These are binomials. Bi is the prefix meaning 2. Just like bicycle, it's bi because it's got 2 wheels as opposed to a unicycle, which has 1 wheel. So what we've taken is these binomials, we've taken powers of them, and we've looked at the coefficients here. So these numbers are called binomial coefficients because they're the coefficients of powers of a binomial. Okay. All right, let's look at, now bring n choose k into things. Oh, which I did say were called binomial coefficients several slides ago, and this is the link. We do have a recurrence relation for calculating our n choose k's. If we start with n choose 0 and n choose n, they're 1. You should do that with the formula to check that. It works out very easily, as long as n is greater than or equal to 0, which is when it makes sense. And, all right, where did that spring from? n plus 1 choose k equals n choose k minus 1 plus n choose k. Is that true? Yes?
Yes, because it's just saying that the 2 numbers above it are the ones that are added together.
That's right. We're going to look at that in a moment, but could you prove that?
Yes.
How would you prove it? Algebra? Yes, yes. Because, and the algebra is not hard, because you have a formula for n choose k, don't you? Yes, you could write out what that is. It's n plus 1 factorial divided by k factorial, n plus 1 minus k, all in brackets factorial. And you've just got to check that it's the sum of those 2 things. And you use your algebra. It's not too hard. It's just adding 2 fractions. Can anybody in this room add 2 fractions? Okay, we have at least one person in the room who can add 2 fractions. I'm really pleased. But you can check that that's true. Actually, there are other really nice ways of proving that that's true, but if I keep on taking too many fun tangents, we'll never get to the end of the lecture. Okay, so you can check that using algebra or various other arguments. But what it means is, and notice that this has been written out. Can you see it clearly? Let's make it bigger so we really can see it easily. Instead of putting in the numbers we had before for Pascal's triangle, we've just put in n choose k's. With n0 on the first row. So the first row is n0. The second row is all the ones with n equals 1. The third row is all the ones with n equals 2 and so on. And we go across. 1 choose 0, 1 choose 1. 2 choose 0, 2 choose 1, 2 choose 2. You see the pattern? You just fill it in there. Well, what this formula that might just fit here says is that, for example, let's choose this one here. Let's see what that formula says about 4 choose 2. So if that says that 4 choose 2 equals something plus something. All right, if 4 is n plus 1, then n is 3. If k is 2, then k is 2, and k minus 1 is 1. So this says that 4 choose 2 is 3 choose 1 plus 3 choose 2. So you put them, take those two, add them, and you get 4 choose 2. In fact, that's what that formula says for every number here. It says each one is the sum of the two, one directly just above and to the left and one above and to the right. It's the sum of those two gives you that. True for all these. That's what that says. Now, the other thing to note is that 0 choose 0 is 1. 1 choose 1 is 1. 2 choose 2 is 1. 3 choose 2 is 1. Just like 1 choose 0 is 1. 2 choose 0 is 1. 3 choose 0 is 1. You'll check that. That's what, that's what that says there, which you can check by the formula. And so what you get is Pascal's triangle again. What we have here, focus, is just Pascal's triangle again. So the numbers in Pascal's triangle, you can think of them as just numbers you get by this adding, this going down and successively adding numbers above. You can think of it as n choose k. We've got all your n choose k's appear somewhere in Pascal's triangle. But they're also the coefficients that you get when you expand your binomials. They're the numbers you get here. And that's only the first few amazing things about Pascal's triangle. Isn't Pascal's triangle amazing? It is. It is really amazing. Okay. So, I did say that you should check that. Now, here's a proof that what was on the previous slide works. Now, you cannot get away with this. The first line says clearly n choose 0 equals n choose n equals 1. James can get away with that because he's unit coordinator and he's an extremely good mathematician. You cannot get away with saying clearly something is true because I won't believe it if you say that clearly something is true. For you guys, if you're doing this, you will use the formula and work out that they're 1. But James hasn't bothered writing it here because it is easy. It's just a matter of putting in the numbers and it comes out. If you do have problems with it though, you will talk to me. So clearly is something that the lecturer is allowed to do and the students aren't. Okay, got that? Life's unfair sometimes, but you know, that's the way it is. Now, we did talk about one way of proving this, and you guys picked it using algebra. You can just put in the formulas, add 2 fractions, and it will work. It's easy. But that's not what's being done there. This is lovely. This is what I call, and what a lot of people call, accounting proof. So let's think about the number of ways of choosing k things from n plus 1 things. A set of k things from a set of size n plus 1. So we're doing it because we're choosing a set of k things, just a set from n plus 1. Repetition is not allowed and it's unordered. This is what we've been doing the last half hour or hour or whatever. And we know the answer is n plus 1, choose k. So we're choosing k things from n plus 1, and the number of ways of doing this we know is n plus 1, choose k. Big deal. But now we're going to do this in another way. This is the sort of thing I mentioned earlier. So let's do this in 2 steps. So I'm choosing n plus 1 things. Think of choosing the last thing. There's no sense of order here, but just imagine you've got your set and you're choosing the last one. It won't matter at the end what order, but you choose the last one. And then we've still got k minus 1 things to choose. So we're going to do it in 2 steps. we're going to choose one thing, which we're going to think of as the last thing, just because it helps us. And after that, we're going to choose the other k minus 1 things. That's perfectly reasonable, isn't it? I could choose a committee of 10 people from this class by choosing the person I will call the last person on the committee, though we know that it actually won't matter once I've got the committee who's last, who's first. It doesn't make sense. All right, so I choose one person, and then I choose the other 9. That's perfectly reasonable, isn't it? It might be a dumb way of choosing a committee, but it works. I choose one person, and then I choose the other 9 if I want a committee of 10. Okay? That's what we're doing here. We're going to choose one thing, and then we're going to choose the other k minus 1 things. Okay. Now, actually, that's not quite what's written there, but but it sort of is. We're going to do this in, let me take I want a little bit of paper so I can scribble. I had one. I swear I had a piece of paper that I could write on. I swear I did. Okay. All right, here's my n+1 numbers. I'm thinking of choosing k things from n things, k things from n+1. I'm actually going to have that is my set from which I'm going to choose k. All right, so I'm going to imagine my things are the numbers 1 up to n+1. All my things are labelled thing 1, thing 2, thing 3, thing n+1. It doesn't matter. All right. I can go 2 ways here because I am going to think of one thing. Well, it might be that we say, well, we can have the last element in our k things. And then I still need k minus 1. So I've decided, what if that last element is in there? And then I need k minus other ones. Well, how many ways can I do this if I say with the n+1 there? For some reason, right at this moment, I like n+1. In how many ways can I choose k minus 1 from the remaining n elements? I'm choosing k minus 1 things, a set of k minus 1 from n. N choose k, yes. But that's a pretty dumb thing to do because I might not, we know that a set of k things might not contain n+1. This just gives all the ones that do contain n+1. All right, we'd better now add to that the number of ways of doing this that don't contain n+1. Right, let's get rid of n+1. I now want k things from n. In how many ways can I choose k things from n? I'm choosing all k things this time, all k from those n. N choose k. Okay. Yeah, you're right. I said k minus 1 and I wrote k. Thank you very much for that. You've saved me. You know I make mistakes. Okay, so this is the addition principle we're using here. I know we've used the multiplication principle, sometimes without saying many times today, but if I'm choosing a subset of k things, I can have n+1 in there or not have n+1 in there. I'm looking at all the possibilities that have n+1 in there and all the possibilities that don't have it, so I've got to add them. Does that make sense? This is something you've got to think right. I'm not doing this followed by that. It's not like breaking a task 1. It's not the sort of thing where I'd write a decision tree. It's the sort of thing where you've got 3 cakes here, 3 biscuits here, and you're asked to choose just one thing. You're only allowed to have one thing with your cup of tea. You've got the number of choices is 3 here plus 3 here, because you're only allowed to take one thing. Does that make sense in that case? 3 cakes, 3 biscuits, you're allowed only one thing with your cup of tea. Your number of choices is 6. 1, 2, 3, 4, 5, 6. 3 plus 3 is usually 6. Okay. All right. So that's the sort of thing we're doing here. We can either have a subset that has n plus 1 in it, or we've got a subset that doesn't have n plus 1 in it. So I'll just put n plus 1 is not in here. Okay. Imagine, if you like, that n plus 1 is coloured pink and all the other ones are bright yellow or something. Just for this argument, imagine that that sticks out somehow. So you've thought of, well, there's the subsets that contain that and there's the subsets that don't. And we find out both and we add them up. And in total, that's the number of ways of finding a subset. Agree? It's a counting argument. The number of ways of choosing k things from n plus 1 is that plus that. And that is what that proof says. That's a counting argument. We've counted the same thing in 2 different ways. We got 2 different answers, therefore they must be equal. And that's the other way, well, the other easy way, obvious way of proving that equality. You can do it by algebra or you can do it by the counting argument. Okay, that I think is particularly lovely. Sometimes you can prove really complicated things easily using a counting argument where the algebra is horrible. Here the algebra is okay. You may prefer the algebraic argument, but sometimes the counting approach is much easier. Okay, you might want to do a bit of thinking about that. If you want to come and talk to me later, that's fine. If you want to understand it, and you're not going to understand everything I tell you in lectures immediately. A lot of you will miss things or forget things or find it's not really lodged in your brain. Get groups of people and talk to each other. Because if you go backwards and forwards and talk and argue with each other and explain to each other, you will make mistakes, you'll fix them, you'll learn. It's much better if you do it in a group. Okay, let's see if we can answer this problem. There are 60 women and 40 men in a class. In how many ways could we form a committee of 3 that is neither all male nor all female? Okay, let's look at a couple of ways of doing this. We could choose a committee of, we want a committee of 3. Okay, that's easy. We can choose a committee of 1 woman and 2 men, or 2 women and 1 man. Okay, that's the way of getting, that's one way of thinking of a committee that's not all one gender. Agree? Okay, so the number of ways of getting 1 man and 2 men is you choose your 1 woman from the 60 and your 2 men from the 40. So that's 60 choose 1, 40 choose 3. And this is 2 tasks because you're doing one task followed by the other. You choose your woman, then you choose your man, and you multiply them together and you get your answer. Okay, well, that's for having 1 woman and 2 men. You've got to do it the other way around. 2 women, 1 man. For 2 women, 60 choose 2 times 40 choose 1. That's it. And then you add them together to get the final answer. Do you agree? Note here that you've used the multiplication principle here, the multiplication principle here, and the addition principle to add them. Now, you might not actually need to think about what the principles actually are, but just beware that sometimes you multiply, sometimes you add and lodge, and it often just makes sense. Practice with simple examples until it does make sense. Okay, that's nice. Oh, this looks like the slide we just had. Never mind, let's just do it. Solution 2. Here's another way of doing it. We want a committee of 3. We could just choose a committee of 3. That's rather large. Oh, it's way too many, isn't it? Because we know that the answer to the question is actually only 117,600. But then If we just choose a committee of 3, some of the committees aren't suitable because some will be all women and some will be all men, and they have to be thrown out. Agree? Right. Okay. So let's find out how many we have to remove. The number of committees that are just 3 men is 40 choose 3, and the number that are just 3 women is 60 choose 3. And these are that we don't want any of those 9,880. We don't want any of those 34,220. So we subtract that minus that is our answer. We look at all possible committees and then we subtract off the sorts we don't want to get our final answer. That okay? Okay, good. And oh, look, we get the same answer. As we should, of course. But it's sort of a bit of a test that we didn't stuff up. And as you've seen, I make mistakes every now and again, not too many, but more than I'd like. And it's always good to do things another way around if you can, just to check that you're right. Okay, so we've done that. And this is a reminder, I must make a short apology to you all. My consultation time is down as the 2 hours after this lecture, and I will be here for some time after the lecture, but I won't be available in my office late this afternoon, which I usually am. Nobody has ever come to see me in my office so far during my consultation time, so I doubt that any of you will really miss that, but I am available pretty much most days to talk to any of you if you want. But the reason that I'm not available this afternoon after about 3:30 is that I'm on a selection committee, and the rules of the selection committee are that they can't be all male and they can't be all female. So, and guess who's one of the token females on the committee? Anyway, so I knew that would remind me. All right, let's look at this a little bit more. Because when you can answer a question in 2 different ways and get answers that are, well, they've got to be the same, but they look different at first, maybe you're onto something. Maybe you're onto some nice little formula, like that one about the one that gives us Pascal's triangle. You know, maybe you're onto something like that. Okay, let's see what we've got. We found that the answer by the second method was the same as the answer we got by the first method. They had to be because they were both correct reasoning. Okay, so just rearranging this, putting these over the other side, we get that thing there. All right, big deal. But if we look at this and say, there's a pattern here if I put in 60 choose 0. 60 choose 0 is 1. Okay? 60 choose 0 is 1. I can certainly put 1 there because multiplying by 1 doesn't change anything. And 40 choose 0, you see, I could put times 1 at the end. 40 choose 0 is 1. So I haven't changed it. But there's a pattern, isn't there? It's not actually. No, it's not. Yep. So we've got 60, 40, 60, 40, 60, 40, 60, 40. There were 60 women, 40 men. 0, 3, 1, 2, 2, 1, 3, 0. There's a pattern there, isn't there? I wonder if that works in general. Okay, well, guess what? It does, otherwise we wouldn't be doing this. All right, now 100 is 60 plus 40, so even better. It looks even better like that, doesn't it? You really, hopefully you see the pattern. Okay, now we can write that using this sum, this sigma. Big sigma means you just add up all the terms. This means you add up terms, and each term is 60-something, 40-something, and you've got the pattern. You start with I equals 0. So your first term is 60, choose 0. 40, choose 3 minus 0. And the second term is when I is 1. And then you have the term when I equals 2. And the last time you write down a term is when I equals 3. So you get 4 terms. 1 for I equals 0, 1 for I equals 1, 1 for I equals 2, and 1 for I equals 3. That's 4 terms. And there they are. See, that's nice. Especially if I do this with something that's going to have 50 terms, you will want to use the big sigma, which says add up terms that look like this with I equals 0, then I equals 1, then and so on up to I equals 3. Okay, more generally, you could try this again with committees of 50 women and 50 men, and then choosing a subcommittee of size, I don't know, 20. That'll get you a very long expression here, but you'll find you get something like this. Whatever you do, that argument will always give you something that looks like this. Now this is an absolute pain to prove algebraically. I don't think I've ever done it actually, algebraically, because if you think about generalising number of women, number of men, size of the committee, the argument that we've just been through of counting things in two different ways gives you this. So here it is. Ooh, there's an error. I can't believe I have looked at this. It's actually Vandemons. I'm sure that's an A. Vandemons. I don't think it's Vandemons. I think it's Vandemons. Anyway, it doesn't matter. If Vandemons. Nobody's going to fry you for getting a letter wrong. We'll fry James though, won't we? Because that's his mistake this time. Okay, but that's it. It's got a name. It's called Vandemons identity. I don't know who Vandemon was, but the identity I do know. Now, all right, something to look at here. We actually can generalise n choose k, the binomial coefficients for n and k, if they're not integers, not positive, and k is not less than n. The context we've done is because we're choosing k elements, a set of k elements from a set of size n, then for us, we've always had k less than or equal to n, and that's when it makes sense. However, one can generalise this and go further, and we are not going to do it here because that's a massive step above mathematically of what we're doing in this course. But the first step you do when you generalise is if k is bigger than n, it's 0. Now, of course, that makes sense here because if I've got 10 people in the room and I want to choose a committee of size 12, how many committees are there? There's none because it's impossible to get 12 different people from 10. Okay? You happy about that? It's like if I've got a bag of 5 blocks of chocolate, and I say, in how many ways can you take 6 different blocks of chocolate from my bag of 5? You say, I can't do it because there's only 5 blocks of chocolate. Doing nothing doesn't help. The answer's not 1 because doing nothing won't get you 6 blocks of chocolate. It's just impossible to get 6 blocks of chocolate from a bag of 5, unless you believe the YouTube video we saw last week. Okay, so that's a perfectly reasonable thing to say, that that's 0. Okay. Why is that important for the above identity? Why is that important for the Vandemond identity?
M plus n can't be greater than, sorry, k can't be, k can't be greater than m plus n.
Very close, very close. In fact, I'm not going to bother doing that if k is greater than m plus n, but it's k could be greater than m or k could be greater than n. So you've almost got there. Yes, yes. You will see, and actually it will also be correct if, in fact, you are strictly correct because there's no restrictions here given for k and m and n, so you are completely correct. Yes. So we can have that greater than that, given the conditions here, because this is quite general. But even if k is less than m plus n, and so it looks reasonable, you can find that one of these numbers, that might be greater than m or that might be greater than n. And that term will be 0. Which makes sense if you think about it. Think about that in terms of committees. You might only want to have 6 women and 4 men. No, take 6 women, take 8 women and 2 men and see how it works out. Just 10 people, 8 women, 2 men. Think about how it all works out. Something for you to play with. And if you play with that, you'll sort of, this identity and the thinking you'll learn from it. Okay, And that's the sort of thing, what happens when we use the identity to expand that? 99 plus 1, choose 3. You'll find that most of the terms are actually 0. So maybe you should do that. Most of the terms are 0. Well, they almost all are, aren't they? Because if we think of 99 women and 1 man, well, you can have 99 women and no men. You can have 98 women and 1 man. And after that, you could have, sorry, we've got 100 people. So, yeah, we can have, oh, let's start at 100. 100 women and no men. You can't have that, can you? No. So that'll give one of your terms will be 0. You can have 99 women and 1 man. All right. You could have 98 women and 2 men. Oh, no, you can't because there's only 1 man. So that term will be 0. So most of your terms will end up 0. Okay. That's if you use the identity. All right. There's some other ones for you to think about. All right. Can you prove van der Mon's identity? Look, he spelt it correctly there. Yes, you can. And the reason is the thinking. Think that you've got M women, N men, and you're choosing K and go through exactly the same argument we went on the previous slide. It's a counting argument. You can prove it. If you want to do it algebraically, I'd love to see it if you succeed because I don't think I've ever bothered to try and I wouldn't mind seeing it. Be very happy to see it. Someone sent me this lovely thing on surjective functions over the last week. That was wonderful. I like getting nice things to read. Okay. Oh, and there's the hint. That's the one I gave you. Okay. That's van der Mon's identity. Now, the Fibonacci numbers. We have this recurrence relation. Ooh. Remember the Fibonacci numbers? We introduced them as the number of ways of climbing a set of stairs, where each time climbing Fn was the number of ways of getting up n steps, and you could do it by either going one at a time or maybe skipping a step. And there's a whole lot of ways you can do that, where you're allowed to just go step, step, or skip steps at times if you want. Every possibility. That was the Fibonacci numbers. We have that recurrence relation for the Fibonacci numbers. And now we have the Fibonacci numbers related to the binomial coefficients. Isn't that amazing? I mean, it is truly amazing. It's sort of come out of the blue. They're totally different things, yet this appears to be, or maybe it's accidental. But certainly, there is a pattern here though, isn't there? 10, 9, 8, 7, 6, 5, and on the bottom 0, 1, 2, 3, 4, 5. Which we can write that way as well. But the fact that you can do it here and there's a pattern makes you think that maybe there's something here in general. Okay. Can you obtain a similar formula for Fn for arbitrary n? That's just fun for you. That's a fun exercise. It's not something that's examinable, but it's fun to do. And if you do exercises like this and play with them, whether you get something out of it or not, you will have learned because you're thinking about the things that are relevant to this course and you're practicing your problem-solving skills and it's all good for you. So I'm leaving that one for you, but it's not an accident. I'll tell you that much. It's not an accident. There's so much interesting stuff that happens. Okay, would now be a good time for a break? No? Okay, we'll vote. How many would like a 10-minute break? How many don't want a 10-minute break? The 10-minute break wins. Yeah, sure. Only one of them.
Yeah, no, just on this
Let's
one.
move over to here where we are. Oh, okay.
So this would be like 27 sorry, 30 shoes 27.
Yes,
Right.
paper, right. Where's my, here's my scrap. Yes, because
So then later I
from
wanted
30
to
we're
try and
choosing
prove
27.
and then I so I tried, and then I was going like, oh wait,
Using the formula.
I know you guys
Which is why it's essentially the same sort of thing.
Yeah, so it ends up being the same.
Right. So it's almost really you wouldn't call it reciprocal, but
That's
choose that one definitely. That makes sense. And then same with these questions. This would be 100 sorry, 100 choose 7.
Yes.
Right.
Yeah, well, the 100 choose 3.
I guess that makes sense because they're mutually exclusive.
Here's the whole 100 people, and I take 3
Oh,
of
so
this
you want one
person.
for
Pull out 3 people.
Well, then how to separate them is to actually select a group of people as well.
Exactly.
Yeah.
Yes, I can choose the 90%. I'm not in the committee.
Right.
Yes, so that's another, that's a way, that's a counting number to go. Yeah, yeah, there's a whole lot of really, really nice stuff.
Just very quickly as well, I was going to talk also about why zero
Okay, why, because I said so, that's the reason I can give them
because zero is strange.
you've got to, you've actually got to think about this carefully. Sometimes it's like the number of functions you can
Yeah.
the number of ways of going up no stairs is 1, do nothing. But the number of ways that you can 5 plus 6 bottles of chocolate for a baby containing 5 is 0.
Yes, that's different.
So 0 can be a bit subtle. On the whole, the way one thinks, you've got to think carefully is there a pattern there that I want to continue? So I've got a trust relation, and I'm thinking about the first step or two. But I've got to think very carefully. Something I really thought about.
That makes sense. You want that consistency.
Yes, I want
Yeah.
consistent. I've got to be consistent. It doesn't make sense just at this base case here, or can I go back one step? Sometimes you want to get the smallest case possible because then you do something because things fly.
Which that also, however, explains why 0 to the 0 maybe 0.1 for these purposes. It's consistent. Whereas with index laws, there might be more normal 0 because then that's inconsistent.
I know. It's just one off.
Yeah, exactly. Yeah. So you're looking at what do I want to be consistent.
Exactly what the note takes.
That's right.
Yeah.
Consistent with
Great.
my but there is another reason for that.
It's a legitimate way of doing
If
it.
I'm counting things and I've got nothing, then I'm starting with nothing.
So you're a bit of a dickhead.
If I start,
Big galaxy road.
the reason is that, it's sort of, it's sort of because
Everyone is going to
one is so that reason, he really doesn't look beyond what we're doing here. And that's,
I think it's making sense.
that's another reason.
You know, it's always fun.
It is.
I mean, as a shorthand, I can remember that 0 is really strange.
Yeah, remember,
Comes up with novel things.
just remember you've got to be careful, that's a really good.
Yeah.
Yes.
So there's half an hour step down.
Choosing making through the plus one. Oh, this one. Yeah. I think this is a little bit of a challenge. It might take most people a while to get their hair. Okay. So let's say I'm choosing. Let's say I'm choosing. Okay, let's just choose 5 balls. And so they're all different colours. But think of this is different. Perhaps we both really like it. Yeah. So in some sense it stands out, even though we're just asked to choose a subset that contains the
What's that standing for everyone?
Oh, everyone. I think
but then there's a
everyone.
whole lot of subsets that don't contain it. So there are two sorts of things. So I'm going to find all the subsets. I'll have to find the number layers and the number layers. Yes. So how many contains a red ball? We've got two. Two has three. I've got four. Yep. The others, I look for yes. So the total number is 42 plus 4 plus 3. Now, it's exactly the same when you've got 1, 2, 3, and then plus 1. Again, it's exactly the same thing. You're going to put this red one here.
This is what's not even. Yeah. Because it takes time. How long does it take?
So you've got two types of sets. Other ones that contain red and the ones
I thought it was the maple had another somebody.
yes, and that takes more examples too. It might be easier to understand this one. That's a very good one. Of course you can.
I'm pretty good. I just really want to make sure I'm what I'm understanding. I know that unordered solution is basically it's like a subset. Basically, when you went to the first example, we did the 5 by 6 because there's 6 permutations in this.
5 by 6 factorial, yes, that's right.
Yeah, because there's you're taking from a subset of sites and there's 6 different permutations within that.
That's right.
Yeah.
This is 1, 2, 3, 2, all those.
So you're dividing it by 6 because you counted that sometimes. Since unordered really doesn't take into account like the working perspective with discrete discounting and pushing out 6 times. That's I'm just making sure that what I understood.
That's correct, yes.
So with the polyfactorial, I understand this part, but you wrote, I said 14, I twisted it. Because I think you wrote 6 times 6, 7, 8.
Exact terms. What did I write? Let's see, did I make a
I think
mistake?
6, I was there.
Okay, I hope I didn't, but you never know. Okay, so we've got our, it's the one where I put down the,
And this makes sense to me as well, because you move it down.
there it is. Yep, that one there.
Yeah, because I was actually a bit confused here.
Oh, it's 8 terms. Oh, thank you.
Yeah,
I better
I
put
was
that up
really
and tell
confused.
everybody. Sorry, no.
No, I was so confused there. I was like, I don't know if I'm just sorry. I don't speak out about it. I was just like, because I thought, did I learn it wrong?
Yeah, I know. You're never sure with who's right. I'll have to show everybody and tell them that I screwed up on that one.
Yeah, because it goes.
Yeah.
Here. Oh, yeah, because the 6 there. I was.
Yeah, I'm going to have to show everyone that I may have got
Oh
that
yeah,
wrong.
because
Yes, thank
that's
you.
essentially the same thing. Well, sorry about this. I'm just
okay.
I'm just gonna 14, 6.
14 times.
Because 8 and 6, yeah, and that's would be the same thing as 14. 14 choose 6 would be the same as 14 choose 8.
Yes, it is.
Because
Yeah.
when you think about it, I looked at it more in terms of like a sort of pictorial way, and I saw that you're doing the same thing, kind of like on a binary S-way when you're like converting the binary.
kind of like that, and I was seeing it's basically the same thing. You just because what you're taking, I look at it like two boxes, and you're taking like one section of the box. But you're taking like one section of the box, and you're pretty much looking at the arrangements of that, and then you kind of. And in the second half of when you do the factorial there, you're kind of taking the instance when you're not counting those possibilities. You kind of get rid of those.
I think I've lost you, but I think you've got it. I think you're fine.
Yeah. It's
think
pretty
you've
much
got it.
you're taking two halves, and then here it's like what's happening. Here it's pretty much it's K. I get what's happening because that's what's occurring. There.
Yep. Okay.
Yeah,
No, it sounds like you've got it.
I feel like I got it, but it's hard to express it sometimes.
It is. It's a real challenge. Writing this stuff down to explain is really hard. The best way to do it is to do 4 or 5 examples so you've got it in your mind, because the challenge is you're not going to have to write down detailed explanations in the test, but I do want you to be able to see it and write down the right numbers. A couple of words of reasoning, yes. We can usually tell from a couple of words whether you're thinking right. It's whether you're thinking right. That's what I really want.
Okay.
It's a whole challenge above that to write some of this out so people can read it.
Yeah, it is.
It's huge. But most of this you won't have to, because people know what n-choose K means. People know what factorials are. People know basic counting problems. That's the sort of thing you're probably not going to have to write out. I just want you to get the problems right, thinking right.
Oh, the concept of it.
Solving. The concept so you can problem solve. And
that's good, because I tend to, knowing me, I tend to really want to understand 100%.
Good.
Though it does wreck my brain sometimes.
Oh, it does. This stuff is because you've got to be really careful, and sometimes it's complicated. Yeah, it's good for the brain.
I know, really.
It stretches it sometimes.
But at least you reckon I'm good doing all that right. But then the part where it's like n plus 1 choose K equals n choose K minus 1. Is it because you're basically what's happening here?
Let's get them a piece of paper and I'll write it. Do what I did with someone else, and we'll scribble over here, and then we'll. Come over here and let's have a look.
This is extension 2, but we it's clumsy.
The minus one is because you were counting that element.
Oh yeah, it's in there.
Okay, then now I got it. Now it's making sense. Yeah, that makes sense. Oh no, the minus one is because you're automatically choosing that one to be in.
Yeah, it's already there. It's like
Oh, okay, yeah, I'm just looking at it, and then now I kind of got it because it's the minus one, and I'm like, no, because you're already saying that's already a possibility, or you already chose it as
Gotta get that.
sorry about that. Yeah, I know.
I think you've got it.
Is there right to keep the paper?
Thank you. Okay, back to work. And I have been caught out. Better get this on the microphone. I have been caught out. On the slide that's up here showing, I wrote the wrong thing. See that 8 here? 14 factorial over 6 factorial is the falling factorial 14/8. So just note that. That should be an 8 there, not a 6. I think I was thinking 6, but it's actually 8 because there are 8 terms in the product. That's the falling factorial is actually 14, falling factorial 8, and I wrote the wrong thing there. So it's a good idea to correct it because it's not true what I wrote. I'm glad when you pick up my mistakes. I need you guys. Okay, let's move on to the last little bit. Unordered selections. You see, we haven't done, there's something we haven't done. So there's a nice little picture of a lot of different coloured balls. And choosing balls of different colours isn't, they make nice counting problems. But of course, there are many counting problems that are the same as choosing balls from a large pit of coloured balls. So we've got a pit with lots of blue, green, red and yellow balls. 5 balls are chosen at random. How many colour combinations are possible? Now, by colour combinations, we mean things like, just at the bottom of the slide, I could choose all yellow balls. Or it could be that I've got 3 green and 2 red. There's a lot of possibilities. I end up with 5 balls, but the colour could be repeated. The order's not important, I'm just choosing balls. So how many colour combinations are possible? So it naturally is unordered, because saying there's 3 green and 2 blue is the same as saying there's 2 blue and 3 green. There's no sense of order. But for the colours I can get, we're just thinking of, if you look at the bag of 5 balls I chose, how many different ones are there in terms of colours? They could be all red or all sorts of things. That's not something we've learnt to count yet. So there's the question. And things like blue, green, red, yellow, yellow is the same set of colours as here. That's the same. If you've got a bag of these and a bag of these, it's the same. You look in your bag and you see 2 yellows and a red and a green and a blue. Okay. So order is not important. But repetition is allowed because in our collection we're looking at colours. We can, for example, have yellow twice, because we could have 2 yellow balls. We could have 3 yellow balls. We could have 4 yellow balls. We could have all yellow balls. So repetition is allowed. So this is what we haven't done. We've done ordered selections with repetition, ordered selections without repetition. We've done unordered selection without repetition, but we haven't done this. So we're going to do it. Here it is. Let's think of having a colour combination. Because we're choosing 5 balls, we'll have 5 symbols. So imagine there should be 5 circles there. I guess if James put 5 circles in all the way, it would probably go off the page. But anyway, actually no, sorry, we've got, overall we'll have 5 symbols or this won't work. And we've got 3, I think of these as dividers. So the way this is going to work is we've decided to write down, this is not important, but we've decided to write down the blue balls first, and then the green, and then the red, and then the yellow. Okay, you could do it in any way, it doesn't matter. But if we have balls, we can decide to line the blue ones up first, and then the green ones, and then the red ones, and then the yellow ones, all right? We could always line them up like that. Okay. So if you've got, for example, 100 balls, then to check that one sack of balls has the same colours as another, it would be a good idea to line them up in this orderly fashion to check. Okay. We might not have any blue balls, that's fine, we might have all yellow. But what we do is we put our dividers between the groups. Because we've got 4 colours, to separate them, I need 3 dividers. I need a divider to divide as a fence between blue and green, 1 between green and red, and 1 between red and yellow. Because there are 4 groups, I only need 3 dividers. Do you see that? Right. And so we represent blue, green, red, yellow, yellow by having 1 ball in the blue here, and then our 1 green ball goes there, and our 1 red ball goes there, and our 2 yellow balls go there. Okay? Now, note that, just looking at that, you can tell me how many yellow balls there are. How many yellow balls are there? 2, yeah. See, there were 2 yellows, right. How many green balls are there? Right, right. Now, you can tell me that without looking at the colours. You can tell me that without looking at the balls. So just the arrangement of circles and dividers tells me the colours. It tells you the colours. It tells us all the colours, doesn't it? So if I was to, cover up those. Want to keep them secret. So this first one here, what are the 5 colours we see on the 5 balls represented by this? How many blue balls do we have? How many green balls do we have? How many red balls do we have? How many yellow balls do we have? All right, that was easy. That was the one we just did. All right, what about this one? How many blue balls do we have? Green, red, yellow. Okay, let's now do, how about this one here? This looks a bit funny. So for this one, how many blue balls do we have? None, that's right, because there's no balls in the blue section. How many green balls do we have? I'm looking at this one. How many green balls? 5. How many red balls? 0. And how many yellow balls? That's 0, that's right, because there's nothing. See, this bit's empty, and this bit's empty. So that means there's no blue, no red, no yellow. They're all green. Okay, so just by the arrangements of circles and dividers, it tells you the colours, doesn't it? And if I give you a string of colours, blue, red, blue, red, blue, you could work out where the circles and dividers go, couldn't you? How many circles would go in the blue section here? And then we put a divider, don't we? How many balls go in the green section? None. So we have another divider. And then we get to the red section. How many balls? And then we have a divider. And how many yellow balls? None. All right. So you see that this arrangement of dividers and balls, each arrangement corresponds to exactly 1 bag of coloured balls. So if we can count the number of arrangements of circles and dividers, we can count the number of colour ways of choosing 5 balls. the colours. Agree? Because they correspond. We've got something that's difficult and we've turned it into something that's easy to count. We know how to count that. Here it is. We've got 8 things to arrange in a row. 5 circles and 3 dividers. So we've got these 8 places here. Now, we've got to look at the number of arrangements of circles and dividers. Okay, every arrangement of circles and dividers gives us a colour arrangement. So what's the number of ways of choosing 5 spaces from this 8 to put our circles? 8 choose. You're right, you're looking ahead. Yeah, it's 8 choose 5. The number of ways of choosing from those 8 spaces, 5 of them is 8 choose 5. Now the reason is we're choosing 5 things from 8, 5 places out of 8. There's no sense of order because it doesn't matter whether I choose I'll have that one, that one, that one, that one, and that one, or whether I say I'll have that one, that one, that one, that one, and that one. The circles end up the same. So there's no sense of order. There's also no repetition because I can't put 2 circles in the one space. So that means what we're looking at is n choose k, or in this case, 8 choose 5. Okay, and once if we've decided that the circles are going there, then that's it, because there are 3 places left and the dividers have to go there. There's no choice then. The only thing we have to do is look at, from the total number of places, in how many ways can we choose 5 of them to put the balls or the circles. And that's it. And this works if you've got 100 balls and 53 colours. It all works. So that's it. We can now do unordered selections with repetition using this little trick. Okay, say we've got only 2 different colours and 5 balls. Okay, well, if we've got 5 balls, each selection can be represented by 5 balls, but how many dividers will I need? 1. Right, so I've got to look at the number of ways of arranging 5 balls and 1 divider in a row. So that's 6 things. 1, 2, 3, 4, 5, 6. In how many ways can I choose 5 places from those 6 for the 5 balls? 6 choose 5. Okay. Now 6 choose 5 happens to be 6. You might look at that and say, well, there's only 6 places the divider can go. The divider can go there or there or there or there or there. There, giving you 6. Same answer? Correct. Correct reasoning. Okay, 20 balls and 8 colours. Okay, I am not going to draw 20 circles. How many dividers will we need with 8 colours? 7. 1, 2, ... 7 of them. Okay, so how many things have I got in total to write out? Dividers and balls, how many in total? 27 things in total, 27. So I've got 27 symbols, so I have to write those in a row. Imagine 27 places here, and I want to put those 27 symbols. Let's do the balls first, as we have been. In how many ways can I choose? There's 20 balls. 20 places for my 27 to put my 20 balls. 27 choose 20. From the 27 places, I choose 20. And the same as before. What we're doing is we've changed this problem from one of balls and colours into one of arranging symbols. And when we're arranging symbols, the way we've rephrased the problem, there is no repetition. because I can only use each place once. I choose a place, I put a ball. I choose a place, I put a ball. I can't put a ball in the second place because my aim is to put them all out in a row. And it's not ordered because it doesn't matter in which order I choose my places. What matters is where the balls are at the end. So it's unordered. So we have turned a problem from one sort of problem that does have repetition, unordered with repetition, into a different problem of arranging symbols that is no repetition and unordered. And we know that for that we use n choose k. And here we've got 27 symbols and we're choosing 20 of them. 20 places in which to put our 20. Okay, so that's a clever trick, isn't it? It is a clever trick. Think of another way to do it. All right, if you do think of another way of doing this ball and colour problem, let me know. As long as it's correct and gives you the right answer. If it doesn't give you the right answer, throw it out. There's something wrong with it. Okay, so what we did was we took our unordered selections with repetitions allowed, and we ended up finding that there was an answer that used n choose k, except that it wasn't our original n and k, because we had to add the fences and so on. So what we ended up doing in each case was having the number of, we're choosing k things, and then from n available things. In our case, it was colours. And because we had n colours, we only needed n minus 1 fences. So we've got k plus our n minus 1. That's in total the number of spaces we have to fill with our circles and our fences. And from that, we chose k places to put our balls. And that's why it's n plus k minus 1, choose k. There it is. Now, I never remember that formula. I remember the trick. Because it's much easier to remember the trick than to remember the formula. If you remember the trick, you can work out the formula. If you've got the formula and you don't have the trick, you can't modify that thinking to do a problem that's slightly different. Like this one. This is the second last slide. Oh yes, the last slide's just for you later. How many solutions to that equation are there? What do you think, everybody? Now note that each of A, B and C, D can be 0 or 1 or 2 or 3, etc. But it can't be negative. Anybody else like to offer an answer or a method?
Thinking about the original example question with 4 colours and 5 balls, that's a similar question because let's say G, R, B, Y as 4 different colours, all
Yes.
going to equal 5 in that instance. You can only choose 5 balls.
Yep.
And in that instance, we did 8 choose 5, which was. So I've got a feeling it's something to do with that.
Yep. Yep. It is. We can do the same thing just like that. I have a feeling if I could wait here for half an hour and we probably wouldn't get too far with most people. So let's think of how I can get numbers A, B, C, D. Because they're whole numbers, any whole number is a certain number of ones. And in fact, in the end, I want 21. So I'm going to write 1, 2, 3, 4. No, I'm bored. All right, so there. Let's say I've got 20. I've written down 20 ones. There's 20 of the ones. These are ones. They're not fences or dividers. These are number ones. Now, I'm going to think of breaking that into 4 groups. The first group will be the number of ones that is A. So if A is 3, then there'll be 3 ones. And then B might be 10, and then there'll be the next 10 ones. Basically, I'm going to divide those ones into 4 groups. The first group will be A, the second B, the third C, and the fourth D. So I'm going to put some dividers, which will be big purple dividers. How many dividers am I going to need if I'm going to divide into 4 things, A, B, C, D? 3 dividers. So I'll have 3 dividers in there as well, somewhere, who knows? All right. And that will represent the number of ones there will represent A, in this case 2. The number of ones there will be B, the number of ones there will be C, and the number of ones there will be D. And we know they'll add up to 20 because I started with 20 ones. Do you agree? So each arrangement, each solution here, A, B, C, D, can be represented by an arrangement of 20 ones and 3 purple dividers. So what we've got is, how many symbols do we have here altogether? 23, that's right. So we've got 23 symbols. Let's do this. So I'm going to put them out in a row. Oh, that's 23, that's a lot of symbols. So I've got 23 places. And in each of these places is going to go one of the symbols. I'm going to arrange my ones and the dividers into those 23 places. Let's do the ones first. In how many ways can I choose 20 of these 23 places to put the ones? Is repetition allowed? Can I choose the same place twice when I put my ones down? No. So no repetition. Does it matter in which order I choose my places for the ones? Like if I put 1, 1, 1, does that matter if I put 1, 1, 1? Because I'm choosing these little places. I'm choosing places. From the 23 available places, I'm choosing 20. So I'm going to have that one, and that one, and that one, and that one, and that one. Does the order in which I do that matter? No, because I end up, whether I choose that one, that one, that one, that one, or that one, that one, that one, that one, the ones still end up in the same place. All that matters is where the ones end up. So it's unordered. So I'm choosing how many places from 23 for the ones? 20. So it's 23, choose 20. And that's the answer, because there'll only be 3 places left over, and that's where we put the dividers. Now, no repetition, unordered, over the page. No repetition, unordered, N choose K. I did use the right thing. And that's what the last slide is. The last slide is just a summary of counting with and without repetition, ordered and unordered. Now, some people like to remember this. I've never remembered this in my life. I think about how you do it, how the multiplication principle, the trick for this. If you remember those tricks and how you do it, 10 years from now, you will probably be able to recreate this table. If you decide to just rote learn the table, next week, it could all be gone out of your brain. In fact, an hour after you learn it, it might be gone from your brain. So the other thing is, if you learn how to think, you're learning techniques to solve problems. Because while we've done a lot of techniques, just another minute, quiet please. While we've done a lot of techniques for solving counting problems, these are the basics. There are lots of counting problems that you can't solve with this because they're harder. Or maybe you can, but you need a lot more thinking. For some, I mean, you get a counting problem. You don't know whether you need a recurrence relation or maybe whether it's ordered selection, or should you use the multiplication principle, or should you use the addition principle, or should you, like the example there, use a mix, or is it beyond all of those? There's all sorts of things. And without the sort of thinking you need, you won't be able to go further either. And it's more fun if you think. And it's better for your brain if you think. You develop more neurons if you think. Okay, next week is the test. Be here a little bit early. Remember, there's no calculators, so you're allowed to forget your calculator. So I'll see you this time next week. 12 o'clock next week, maybe a bit early. Ready for your test. Do lots of tutorial questions, and I wish you luck with your study. See you. I'll see you next week. Only for 12 o'clock. Yeah. Let's move away from the microphone.
I don't think so. They would have to
Yes, I think one.
It's week 1 to 4. Sorry? Week 1 to 4 within the week. I think that's James sent an email, and I think it came out today. I think that's what.
Yeah, that's right. Yeah, I did have a look at that.
Oh,
yeah, that's where I was getting it from.
It's week 5 today, isn't it? The next week's week 6. So
Yeah, that's right.
yeah, that's given you the time to sort of do the 2 questions and sort of thing. But it's in James made it really clear in his email. I remember because I saw the email.
Yeah, so the announcement is as well.
I don't think it's checked for this guys. It's probably put it later.
I think he only put it up today.
I think it was today.
Yeah.
Oh, that's fine.
Yeah.
Yeah, no, because it wouldn't be fair to cover a section that we haven't gone through to talk about yet.
No.
It wouldn't be fair.
It wouldn't be fair, no.
Exactly. But no, I'm getting all this.
It's fun.
Yeah, it's making sense.
Yeah,
Yeah, no,
there is a lot you think about. Often there's a lot of things about, but it's fun.
Yeah.
Yeah, true. It's fun.
There's so many like puzzles and questions throughout my life where I'm like, oh, and a bit of accounting theory. I remember once I spent like 2 hours one Christmas, and I was maybe teenager, like 14, and I had a children's book that had 7 sections that you could flip over. You know, one of those ones. And then millions of different stories. And I was trying to figure out how many different combinations were there. And of course it took like an hour or something.
You did it.
Yeah. Yeah, it was fun. So good to know it all makes sense. Anyways, thanks very much.
Yeah, good luck for next week.
Thank you.
Yeah.
You have a good day.
I'll be around anyway before if anyone wants to drop in.
Yeah, but you have this video, don't you?
That's just this evening.
Is this the thing?
Yeah, we're starting now late because it's got this people from France joining.
Oh, France.
Yeah, it's an interview only, but there's some candidates from somewhere in Europe anyway. So we often do video conferencing, and when you video conferencing, I hate the US because you've got to get really early for them. I don't mind Europe. I don't mind Europe because that's later. Correspond with colleagues in Europe, that 9 at night where we are. But I hate the US because we've got to be up really early to.
Yeah, no, I know someone in Chicago. It's technically 8 hours difference, but it's technically 16 hours difference where I'm in. But it's like you have to
just change because of daylight saving anyway.
Yeah, I know. See, I'm pretty sure it's 8 hours. Like I always say, like they're 8 hours ahead. No, that's not correct. 16 hours behind.
They're behind. Yeah, they're behind.
Yeah. But I'll just say 8 hours ahead because it's pretty Chicago. That's the only reason. Even though I know it's 16 hours behind.
Exactly what you mean.
Yeah.
Be sure to take out context. You have the US.
Question. Oh, it's really a good question. Take it out.
It's still being recorded.
Oh, really?
We're still being recorded.
Anyway, I'll let you go because there's other people I assume that would want to talk. So.
Yes, I'll see you next week.
See ya.
Yes. I just had a question about the triple manual.
It should probably start.
Yes, okay, let's get a piece of paper. Is this one?
It was in the
I'll get a clean piece of paper. Actually, I think I can turn that off.